Hi, this is Lester Martin from Hortonworks University, and continuing on in our Hadoop's Essentials course is this next module focused on defining and understanding Yarn and the architecture that makes it up. And as the tagline says, this is Hadoop's compute framework. So I want to keep in mind that Hadoop core is storage plus compute. Storage represented by HDFS, and compute is ultimately represented by Yarn. So we'll run through the primary component types here, masters, worker component types, and then job level component types. We'll make sure we understand what a container is and what the concept of requesting and what the process and the attributes are when we request containers or resources. And then we'll finish up with this exploring some of the multi-tenancy controls that exist that are bundled under the name capacity scheduler. So a quick high-level overview. So Yarn, if you're not familiar, stands for Yet Another Resource Negotiator. A little bit of a play on words and letting engineers name things for you. We always get interesting names. So to talk about Yarn, while I don't really love to talk about history of, and sometimes I think Yarn warrants a good history conversation, we discussed in an earlier module the MapReduce framework. We understood it from concept, we understood it from how code works, that concept, etc. And we talked about blocks and processes that were mappers and processes that were reducers. But ultimately, MapReduce has been there as long as Hadoop has been there. Again, it's it was the original compute side of Hadoop core. And what we're trying to show in this slice here, we call that, we used to call it Hadoop, but now we call it Hadoop 1. And obviously we had HDFS, we still have HDFS, but we had one programming model, one runtime workload model. It's called MapReduce. And MapReduce took care of resource allocations and monitoring across this entire grid, as well as that very specific one workload type. And then additional frameworks such as Hive and Pig latched on and bolted on top of MapReduce. So in the realization of how do we get past this and how do we scale a number of things, how do we allow additional workload types beyond MapReduce so folks don't just build a peer that sits on top of HDFS, they leverage some kind of framework to help them. We took MapReduce and decomposed that into this notion of some cluster resource management functionality we call Yarn. And then what was left was the programming model called MapReduce. And that model, MapReduce, could plug into Yarn, and then other models, other workload types, as you see here, of NoSQL systems, streaming systems, search systems, etc., could bolt into Yarn itself or layer on top of. They could still layer on top of MapReduce. So Hive was a great example. Hive still can run an execution engine called MapReduce, but it has other execution engines such as Test, and definitely applications can, again, use Yarn directly. So I think that little bit of history helps, especially if folks on your team have been in the Hadoop space for a number of years and have that additional information. So this picture is right off the Hadoop.apache.org site. When you kind of drill down and on the main project page, try to understand a little bit about Yarn. We are going to explore all these types here in a minute on subsequent slides. So I'll mention them here and we'll see them in action. We definitely have a master process called Resource Manager. He's our traffic cop. He's the person that's going to be asked for, can I do this, or can I do this there, etc. And he's going to ultimately have to decide, is that okay? On the workers, which we're trying to symbolize in this tier here, workers run a process called the Node Manager. And they're going to be responsible for, as they sound, managing that node, the resources of that node. They will only be asked through the Resource Manager, hey, could we run this size of an environment? Are these amounts of resources available to me to turn around and give out to someone else? So they'll be heavily participating with the Resource Manager. And then the real secret sauce here, in addition to what I explained on the last slide, where MapReduce as a programming framework kind of decoupled and had resource management and workload management itself. In the original days, that workload management was a master task, and that itself caused a little bit of a scalability problem, maybe 2,000, 4,000 nodes. kind of a scale issue because we put so much of burden up in the center. So we decentralized the execution of particular jobs now. A job could be a MapReduce program. It could be a Hive query. A job could be a long-running service such as HBase that's going to start and run for basically forever, or Storm or something. So we decentralized that, and we'll talk about that in more detail, but those will be per application, and they will run actually out in the grid themselves. So you kind of see that if you look really close here, we'll show that in a little more detail here, the fact that, and that lets us scale way beyond those early those early thousands into the tens of thousands. So I don't have an exact published number, but we're scaling much beyond where we were at that point in time. So let's take a little deeper dive in the resource manager, the node manager, and the app master itself. So quick reminder of that overall, where do we see ourselves fit in, and you see Yarn square in the middle of everything, I think. So we'll just slide that over there. And I think we talked about most of these things. It is the architectural center for sure. It definitely enables multi-tenancy. So by default, we're going to run. Anybody and everyone can run, and we'll cover at the end this concept of multi-tenancy so that we're not living in a first in, first out kind of queue. So we can support lots of people, but we have to put some kind of controls in place if we want to guarantee folks can live together. So let's focus on for a bit just what it means to get a job up and running. Again, a job could be a batch application, or it could be a long-running service, or something in the middle. So we saw something like this early on where these are our masters, maybe some utility nodes, and then I had maybe a page or two of worker nodes to symbolize that's your grid for the most part. You'll have lots. So we'll just have a thin row, and then the 2 points to call out are there is a single master process called the resource manager. Now single, there are, just like we talked about with HDFS, they are high availability configuration options, and they're very straightforward, and Bari helps you load those down. So I'm going to have to let you trust me that we have a good solid HA solution in this space, and we really won't explore that other than maybe a conversation on the side. So the resource manager is the person that is asked for resources, as it sounds, and he interacts with many node managers, and node managers are out the workers themselves to decide what can be shared, when, where, why. So we'll focus on the node manager for a moment in time. And as it sounds, we talked about this already, he is responsible for resources, and we'll just talk about resources for right now in the guise of CPU, cores, and how much RAM is available to be granted out for requests. And definitely there's a lot of protocol, a lot of handshaking, a lot of check heart beating, etc., and validation checks and stuff that's happening between the node manager and the resource manager. But what's really going to happen for a job to run, a batch job, a long-running task, is some client. And we don't show the client in these slides, but on that very first picture, for something to start, there is a kind of someone outside the cluster saying, hey, please start this. Now that can be run from a Bari, it can be run from lots of things, but that request has initially come into the resource manager, and it says I have this type of application, or what we call an application master, that I need to run, and it will have to ask for some kind of resources itself just to get started. This is that notion of per job being deployed out to the grid. So what we're trying to show on the top there is that, in fact, that initial request to stand up a concept or a slice of resources, and we'll refer to that a unit of, a chunk of resources as a container. I think I have a slide to kind of reiterate that in a moment, but a container is really just an amount of received, a requested amount of resources that the resource manager said, yes, you can have those, and they can run on node manager 1, 2, 3, 4, 5, 99, 1000, whatever that location is. And then that initial client will actually work to the resource manager, and the resource manager will spin that up from the node manager. The resource manager, while we are decentralizing applications to run out in the grid, the resource manager does keep track of at least where those application masters are. Doesn't really know what they're doing, but knows where they are. And that's primarily in that whole high availability model to handle what if something failed and can it get restarted, etc. So a container. A container is, as I said, is a slice of resources. We'll talk about RAM. Almost always we'll think of the term RAM, and then because today at least CPUs, you have to enable CPU requests to be managed. At its most trivial approach, the resource manager and node manager will allocate based on RAM. So if you had let's just say 196 whatever gig of RAM, then if someone asks for 10 and someone asks for 10, well, I still have 80 gig available to return out when needed. And these containers, many containers will come together to run a application master. Again, the application master's an application master job. There'll be one application master for a job. That job may need 10 or 20 or 100 containers to get done. Just to tie it back to what we said earlier around MapReduce, for a MapReduce job against a file that has 20 blocks, then I'm actually going to, at this point, burn about 21 containers. One to manage our app master, then 20 additional that are having to get spawned off and run. So there we go. We got started. We initially cranked up a container because the client asked for it. The node manager is going to look at all containers the same way, making sure that they stay within the bounds that they were requesting. If they wanted 8 gig, but they transitioned to 12, 16 gig, then the node manager has the ability and the rights to go ahead and kill that particular container. When a job gets started, that very first container, again, will embed within it this notion of an application master. So containers are not application masters, but application masters live within containers. Ergo, not all containers are application masters. Application master is a specific piece of code that comes along and initializes that particular application. Now, people write application masters sometimes as frameworks. MapReduce has an application master. Tez has an application master. HBase can be written to have an application master. Your own distributed grid-aware technology kind of his own application master. You can write one, but those are more often not something you think of as a business application. You think as a technology application that we use for business purposes. And he's the guy that owns the running of a particular job from start to finish. Again, finish could mean don't stop. So he's the job. He has the responsibility, if I need 10 containers, to ask for 10. If 2 go away, to decide what to do. So 2 failed. Decide, do I ask for 2 more, or do I just report that there was a problem? That's really on that application master. And the whole notion of elasticity, up or down, is owned by the application master. Yarn's resource manager and node manager are there to respond to requests and hand out resources, but they don't know what your application is doing, and they don't really need to know. They need to honor the request and be fair, reasonable within the controls that you define. But it's up to an application master to make those choices. That's what we kind of mentioned there at the bottom. So we're still very early on, but it'll move on much faster now. So the application got started. The application master is running within a container, and now at this point, the application master says, you know what, I need a couple containers. He'll ask the resource manager, hey, I need 2 containers of this particular size. He says, sure, here's where I want you to run them. Now we're showing generically node manager as a concept, not as this is one machine. There may be if there are 20 workers or 20 node managers. So the resource manager is telling the app master very clearly, hey, run container 1 on this node and run container 2 on and maybe another node. So it'll look like it's all run in this one box. So I want to make that call out. So at this point, the app master can then talk to the node manager that the resource manager told him to and say, hey, I need a said container. And then he'll allocate that space, get his process started up, and kick that off. And then same thing. He was actually asked for 2, so he spins up yet another container. So resource manager managing the requests, yes or no, can you do this? Node manager, we're working in conjunction with resource manager, so the resource manager can fairly and rightly hand out resources, allocate resources to a particular application, and then the applications can then go fulfill those requests through the node manager that the resource manager granted. How might that look at runtime? How might that look across a very small cluster with 3 nodes, 3 worker nodes, and truly running 2 jobs, 2 application masters? So what we show here is a container in blue, and it's labeled job 1 app master. So that is, again, everything that runs in your worker will be demarked as and considered a container, including these containers that include app masters. This app master is going to work with and negotiate from the resource manager that, hey, he needs 2 containers of these certain sizes. And ultimately, the resource manager said, sure, run them on node 1 and node 2, as you see there. So that's job 1, task 1 at the top, job 1, task 2 in the middle there, right next to the container. Off and running, that's all it needs. Simultaneously, soon thereafter, whatever, and another job is getting started. We're going to call that job 2. Now, job 2 has to have an app master. The app master, it was decided, should run in a container on node 3. And he, like job 1, needs a few resources. So he's going to ask for them and then run them where granted. So kicked one up on node 1, kicked another one up on node 1, and then, as you saw, several more on node 3, and then maybe an additional one up on node 1. Now, that doesn't mean that's how that would lay out. That's just how this particular set of requests happen. And what you're also seeing is there's still free capacity on all these nodes, so Node Manager could satisfy requests. If someone asks for a something this big, right here where my mouse is, then it won't fit on here, and here it'll have to be on node 2. So that's where you would expect those requests to happen. So imagine this not at onesie twosies, or not even 10s or 20s, but maybe hundreds or even thousands of jobs and applications running at the same time in your large cluster. Quick call out is, it may look arbitrary, but ultimately the app masters themselves are trying to run for the purpose of data locality that we mentioned early on in HDFS, that we can know where particular data exist. App masters are more than likely asking for particular places to run their containers that will be on the same nodes that they're copies of the data they need to ask for. So how might that look? Well, I guess I missed a slide, sorry. So the resource manager we had out of the picture, we kept talking about how we ask questions. I just want to make sure we know that resource manager has a lot of responsibilities. This suggests a few of the key ones, but the one in the middle is one we've been talking a lot about: knowing what resources are available, knowing how best to spread that love if wild carded about where things should run, etc. But it also runs this concept called a scheduler. We're going to talk about that next. Schedulers really are opportunity to encourage or allow a good, consistent use with multi-tenants. We talked about everyone can run here, but it's more of a without any additional configuration. We've created a FIFO, first in, first out queue model. And then, while we're not going to spend a lot of time on it, it's very important for multi-tenancy, for lots of other things. We can control security on these kinds of queues and concepts as well. We want to make sure that only certain people ask for those types of resources in those particular capacity queues that we'll describe next. Okay, so all this picture shows is what we just said. Many people are kicking off apps, hungry, reckless, and sneaky folks doing their workloads across this grid. And we need something more appropriate than just simply a first in, first out, since App 1 may, in fact, consume 100% of the resources and need them, for a while. Waves and waves of requests, and App 2 and 3 end up sitting behind. So it doesn't hurt to make sure we get what we talked about earlier, the resource requests themselves. When people are asking, when application masters are asking for additional resources to run themselves, they're talking about priority, they're talking about resources, and they're talking about where to run that. So it's best to kind of see an example, priority for sure, capacity, we're almost always going to ask for amount of memory, and we may or may not be asking for additional things such as cores of CPU, network, etc. But we'll always honor that memory, because that's where we originally started from. Then we have a kind of a resource name. This is that notion of, do I care where this container is, and ultimately how many containers of those characteristics. So if you don't care, if you just have a compute heavy, you're not tied to the storage, just you can wildcard things, you can supply a list of, I'd like to run on, if you were a mapper task, if you were a MapReduce app master, and you need to run an app, a mapper, you might make a request just for that one mapper and say, hey, I'd like it to be on one of these 3 nodes. That's where maybe the copies of the replicas of that particular block are. And make it in that part of the request, you'll actually even say, "I'd prefer it to be these three, but I'll take anything," because you'd rather run than not run at all. Data locality is important, but it's not going to stop you from executing your job. So how do we ultimately get together? Well, we showed a minute ago that the resource manager has many sub-processes. One of them is this notion of a scheduler. And what you'll see in the very next slide is the fact that we create this kind of tree, this nested tree of the way we control access to that is around percentage of slices. So let me just kind of show you that. And there's my phone. So, multi-tenancy with the capacity scheduler is based on this notion. That was the same picture here, this notion of queues, is this nested set of queues that have to that are declared in percentages. So it's hard to see here, but we're saying the data warehouse has 70%, the ad hoc has 10%, and maybe the whatever that marketing department has 20%. So we're building a tiering of a tree of folders here of queues here that are identified by the whole, a percentage of the whole. What really you can kind of get the impression that marketing should get about 20% of the resources, and the data warehouse folks should get about 70%. And that's how ultimately we're going to prevent people from overrunning each other. Now we're going to be able to configure this, should we like it, to let things take advantage of an idle cluster. So if marketing only gets 20%, but no one else is running, you could configure it, and you might often do configure it to that marketing can actually span up and scale up and consume more resources. When you do that, we have to think about this notion of SLAs. What happens when the data warehouse comes along and needs resources, and you're running, that marketing job is running? Do we turn on preemption or not? Which just simply means we give marketing a very short window to step away, or we go ahead and kill those jobs, or do we let them without preemption just finish up and then let the data warehouse manipulate that? And the reality is you have to work with that. You have to work on some of these values to find what the right answer for you is, but definitely this notion of slicing up and percentages is going to go a long way. And what's kind of nice about this, one thing that for sure is, let me go back one slide, is this notion of while capacity scheduler doesn't necessarily have a real rich chargeback system, the data that would drive a rich chargeback model in your organization based on cluster resources across teams, departments, whatever you're doing, however you're sharing this cluster, that information is ultimately coming out of these jobs and how they're working through the queue. The great news for managing these queues is twofold. One, that's something that's always been there, are that queues can change. These definitions, these limits, who's in, who's out, how much they can or can't have, has always meant a runtime configuration. It's easy to make those changes and say, hey, from now on, here's what I want them to be, without any kind of restart. But and that's critical. That's a cornerstone element. And then something that Embari has recently come along with is a rich visual tool for defining these queues and their limits and doing lots of checks and balances. Prior to that, we took this information, we massaged it into a set of key value pairs, ultimately an XML file, and then we pushed that into the queue. We pushed that into the cluster, and we hope we did it right because there was no error checking. We got past that now. We have a rich set of tools here in Embari to make managing your capacity scheduled queues much better. And then just a recap to see if to drive it home with some real, with an example. So we have a cluster, 16, 3, 6, 9, 18 nodes, I guess, across the bottom. And what we're really going to say is let's define three primary root level queues, root level tenants, and they're just your three different lines of businesses that maybe your organization has decided, and you kind of see the slices where A gets a little more than B gets a little more than C. And we applied those particular high-level queues against that. Again, you can control, is that a hard limit? Is that a hard upper limit? So you have this notion of soft and hard limits that you can put on all these different queues. And again, what I meant by that is, can I use more if available at that given time? And when you do that, you do have to ask yourself about, preemption or not. How rigorous are you going to be when that request is using more then the queues are defined, and how aggressive am I in taking that back. So we have to play with that to find the right answer over time. But these queues always have to equal up in the percentages, and we're not defining queues that go to particular machines, as you kind of see here. We're talking about a percentage of, so that can be all over the place, and it could be job to job. It just means at the end of the day, all the requests for line of business A should be, representing this amount. In our case, about 50% of the cluster, not particular queues, not particular nodes per se. And each queue can always be broken down to sub-queues, and sub-queues can break down to sub-queues. So it's a tree of, now, how far is too far? Well, I don't know if I'd want 10 deep for sure. That would get a little bit arduous to imagine. And you probably need a cluster of some certain size and scale to really support that many slicing and dicing of. But what we really said is that big 50% for line of business A, let's slice it up pretty evenly for divisions A, B, and C within that line of business. And again, we have to do percentages of the whole. So 33, and 34% is what we're going to see, something like that here. All right, so we got to the end. Let's run through a quick knowledge check and summary, and we'll wrap this up. So master nodes and worker nodes. What are those processes that exist? One of the primary processes, it was the resource manager for the master. And again, one or many from a high availability perspective, but logically one resource manager, and then a node manager process for every single worker node. All right, which container resource type are we really at a minimum thinking about requesting? That is going to be memory. We might ask for more cores, we may ask for a certain amount of network bandwidth, etc. But definitely the memory request is going to be the initial primary driver about where could this particular container be instantiated. How about this? When application masters, because they have the word master in the name, they must execute on master nodes? Of course not. Application masters, as a refresher, are that way to delegate out and decentralize the running of a particular job. And they run on worker nodes in the context of a container. So from the node manager perspective, an app master is just another container. It's just that it has a little bit more responsibilities to ask for more containers. So who's responsible for dealing with a container failure? So it's not the resource manager or the node manager's job to know what to do when a container fails. Yeah, they need to take advantage of that and update their count so that other things can run, etc. But the application manager specifically has to decide what should it do if one of those containers fail. Do I replace it by asking for another one? Do I wrap the job up early? Do I, that's really dependent on what that application master is trying to do, and has total freedom to act upon that. That includes just generally scaling up and scaling down as well. And I guess last question, we were just talking about this, does the capacity schedule, those queues that we define, those evenly spread queues, are they aligned to specific worker nodes? They're not. We actually have a nested set of queues there, and each level of the queue has to equate to 100% of all resources. And those that have thought about or heard about this concept called node labels actually is a way that we could, with some additional configuration, implement something like that, where a particular queue is aligned to specific machines. So there is, just like everything in Hadoop, there's a way to continue to configure it and turn it and do something more. So I did want to throw that out in case you had heard about that information. So the summary is what we just talked about: app masters being responsible for that for the job, the batch, or whatever that job is, and making sure all the resource requests are made. And they don't always have to be at the beginning; they could be at various times, and dealing with failures, etc. We talked about capacity scheduler being the cornerstone, not just from that first bullet. Yes, many workload types for sure can run in Yarn. Many people from different departments can run in Yarn, but the capacity scheduler is going to be that. More that traffic cop of making sure we play nice with each other. And I don't steal too many of your crayons, you don't steal too many of mine. We make sure that works out. And for sure, we ran through the resource manager, the node manager, and those steps. And those are worth taking another look at some point in time. And hopefully those slides will help make that make some sense. All right, that's my coverage of the yarn architecture and the Hadoop Essentials, and we'll continue on with another module in just a moment.